March 17, 1941. Mare Island Naval Shipyard, Vallejo, California. Ted Nelson crouches in the humid darkness beneath the wooden deck of USS Trigger, a submarine under construction in Building 23. His flashlight illuminates a scene of controlled chaos. 3 welders work overhead, their torches casting dancing shadows on the steel hull. 4 more men stand on scaffolding 15 feet below, wrestling with heavy nuts and bolts. Nelson watches as they struggle to align a threaded bolt through the deck above, their hands moving in the confined space like surgeons performing an operation in the dark. The task appears simple. Attach wooden deck planking to the steel frame below. But the Navy's approved method requires through bolting. A welder drills a hole through the wood and steel. Another welder threads a bolt down from above. Below deck, men on scaffolding catch the bolt, slide on a washer, thread on a nut, tighten it with a wrench, then tack weld the nut to prevent it from vibrating loose. The process takes approximately 45 minutes per bolt. A single submarine deck requires 2,800 bolts. Nelson does the mathematics in his head. 2,800 bolts multiplied by 45 minutes equals 2,100 man-hours just for deck installation. 126 man-days. Nearly 4 weeks of work. He watches the scaffolding crew struggle with another bolt. 1 man holds the flashlight. Another positions the washer. A third threads the nut. The 4th operates the wrench. 4 skilled workers performing a task that should require 1. The inefficiency burns in his mind like a welding arc. Ted Nelson earns $11 per day as a civilian welder at Mare Island. He repairs battle damage on ships returning from Pearl Harbor. He fabricates steel components for submarine construction. He works 12-hour shifts 6 days a week. He understands metal, heat, and structural integrity the way other men understand baseball statistics. And watching this ridiculous ballet of bolt installation, he knows there must be a better way. The scaffolding alone represents massive wasted effort. The shipyard constructs elaborate frameworks beneath every deck, sturdy enough to support 4 men and their tools, positioned precisely to allow access to bolt locations. The scaffolding takes 2 days to build, must be moved as work progresses, and obstructs other construction activities. Remove the scaffolding requirement and you save not just time, but also labor, materials, and workspace. Nelson climbs back topside and returns to his welding station. The idea germinating in his mind refuses to leave. Stud welding exists as a concept. The Germans pioneered drawn arc stud welding in the 1930s for attaching insulation pins to boiler walls. American manufacturers use it for limited applications in horizontal positions. But conventional stud welding requires loose flux powder to protect the molten weld pool from oxygen contamination. The flux powder works fine when welding horizontally. Gravity holds it in place. But try welding vertically or overhead, and the powder simply falls away, leaving the weld pool exposed to air, creating porosity and weakness. Naval construction demands welding in every position imaginable: horizontal, vertical, overhead, at compound angles. The wooden deck attaches to horizontal steel frames, but submarines contain hundreds of other attachment points, requiring fasteners welded at all angles. Pipe hangers, cable supports, equipment mounts, valve brackets. Each location presents its own geometric challenge. The Navy's through-bolting specification exists because no welding method works reliably in all positions. That night, Nelson sketches ideas in a notebook at his kitchen table. His wife, Dorothy, glances at the drawings and asks what he's working on. A faster way to attach things, he tells her, a way that doesn't require scaffolding. She nods and returns to washing dishes. She knows better than to interrupt when he enters problem-solving mode. The solution arrives at 2 a.m. when he should be sleeping. Instead of loose flux powder, encase the flux in a disposable ceramic cap. Attach the cap to the end of a threaded stud. The ceramic holds the flux in position regardless of orientation. The welder presses the stud against the steel surface using a spring-loaded gun. an electrical arc melts both the stud and the base metal. The ceramic cap disintegrates from the heat, but the flux performs its protective function during the critical moments of molten metal fusion. When the arc stops, the stud is welded permanently to the steel. Total time elapsed: less than 1 second. Nelson refines the concept over the following week. The gun needs a spring mechanism strong enough to maintain consistent pressure, but gentle enough to allow precise positioning. The electrical circuit requires a timing device to control arc duration. The ceramic cap must contain exactly the right amount of flux for complete coverage. The stud design needs a small projection on the end to initiate the arc. Each detail matters. On March 24, 1941, he submits a formal proposal to his supervisor, Navy Lieutenant Morrison. The meeting lasts exactly 4 minutes. Morrison barely examines the drawings. Nelson explains the time savings, the elimination of scaffolding, the increased weld strength. Morrison interrupts before he finishes. "We have established procedures, Mr. Nelson. The Navy operates on approved specifications. If you want to weld instead of watching bolt installation, stick to your assigned duties." The discussion ends. Nelson tries again, approaching the shipyard's chief welding engineer, a civilian contractor named Harrison Hartwell. He demonstrates his calculations, showing how stud welding could reduce submarine deck installation from 2,100 man-hours to fewer than 50 man-hours. Hartwell listens politely but dismisses the idea with bureaucratic inevitability. "Son, people considerably smarter than you and me have attempted to solve this problem for 2 decades. If the solution was that straightforward, someone would have implemented it already. Besides, the Navy maintains specifications. We cannot simply modify procedures because a welder has an idea. You need approval from the Bureau of Ships in Washington. You need engineering studies. You need prototype testing. That process takes years." "We do not possess years," Nelson protests. "We need submarines immediately." Hartwell shrugs. "That is not my problem, Mr. Nelson. My problem is constructing boats according to approved specifications. Your problem is performing the welding work you are compensated to perform." Frustrated but undeterred, Nelson makes one final attempt through official channels. He writes a detailed letter to the shipyard commander, Captain Thomas Withers, explaining the current inefficiency and proposing the stud welding solution with estimated time and cost savings. He submits the letter through proper procedures and waits for a response. 3 weeks pass. No response arrives. Nelson realizes the Navy will not listen, not because his idea lacks merit, not because it won't work, but because innovation requires disturbing the established order, and established orders resist disturbance with tremendous institutional inertia. The Navy operates on specifications written years earlier by committees in Washington who have never stood beneath a submarine deck, watching 4 men struggle with a single bolt. On April 15, 1941, Ted Nelson makes a decision that will alter the course of naval construction. If the Navy will not implement his invention, he will build it himself and force them to take notice. He begins working evenings and weekends in his garage in Vallejo, constructing a prototype stud welding gun from salvaged parts. The spring mechanism comes from a junked car suspension. The electrical contacts are copper bus bars from a demolished building. The gun handle is shaped from a piece of oak. The ceramic flux caps he molds himself using powdered flux and high-temperature ceramic clay, baked in his kitchen oven. By May 1941, he possesses a functioning prototype. He tests it on scrap steel in every position imaginable: horizontal, vertical, overhead, at angles. The gun operates flawlessly. A stud welds in less than 1 second. The weld strength exceeds that of traditional through bolts. Most importantly, it requires no below-surface access, no scaffolding, no second worker beneath the deck. One man with one gun can install attachments faster than a crew of 4 using conventional methods. He brings the prototype to work and demonstrates it to several welders during lunch break. They react with immediate enthusiasm. This is going to save us enormous amounts of time, one remarks. You need to show this to Morrison, another suggests. Nelson shakes his head. I already showed Morrison. He expressed no interest. Then quit and start your own company, a third welder advises. Sell your gun to shipyards across the country. You will make a fortune. The idea had not occurred to Nelson. He is a welder, not a businessman. He has no capital, no manufacturing facility, no business experience. But the more he considers it, the more logical it becomes. If the Navy will not use his invention, perhaps private shipyards will. The Kaiser shipyards in Richmond are expanding. The Bethlehem Steel facility in San Francisco is hiring. Shipyards operate up and down the West Coast, all facing identical labor shortages and production pressures. On June 20th, 1941, Ted Nelson submits his resignation to Mare Island Naval Shipyard. His supervisor attempts to dissuade him. Nelson, you are a competent welder. Do not throw away a steady job for some impractical invention. But Nelson's mind is made up. I am going to manufacture welding guns, he tells Morrison, and when the Navy returns requesting to purchase them, I hope you remember this conversation. He departs Mare Island with $11 in his pocket, a garage full of tools, and a conviction that his invention will succeed. He incorporates the Nelson Specialty Welding Equipment Corporation on July 1st, 1941. He borrows $95,000 from the Reconstruction Finance Corporation, a government lending agency established during the Depression to support small businesses. With that capital, he rents a small workshop in Vallejo and begins manufacturing stud welding guns. The first months prove difficult. He has no customers, no reputation, no distribution network. He makes sales calls to local machine shops and small fabrication companies, demonstrating his gun and explaining the time savings. Most remain skeptical. A few express sufficient interest to try a demonstration unit. Slowly, gradually, orders begin arriving. By September 1941, he has sold 18 welding guns and several thousand flux-capped studs. Revenue barely covers expenses. His savings dwindle. Dorothy takes a job at a local market to help with household expenses. Nelson works 18-hour days, manufacturing guns during the day and making sales calls in the evening. Then on December 7th, 1941, everything changes. Pearl Harbor. The Japanese attack destroys or damages 8 battleships, 3 cruisers, 3 destroyers, and 188 aircraft. 2,403 Americans die. The United States is at war. Suddenly, shipbuilding is not merely important. It becomes a matter of national survival. Within days of Pearl Harbor, the shipbuilding industry explodes into frantic activity. The Kaiser shipyards begin constructing Liberty ships at unprecedented pace. Mare Island Naval Shipyard receives emergency orders for submarine construction. Bethlehem Steel and other private yards start operating triple shifts. Every single facility faces the identical problem. How to build ships fast enough. Traditional methods are too slow, too labor-intensive, too wasteful of precious time. Ted Nelson's phone begins ringing. Shipyard purchasing agents who dismissed his invention weeks earlier now want to place large orders. The Kaiser shipyards order 50 welding guns and 10,000 studs. Bethlehem Steel orders 40 guns. Even Mare Island Naval Shipyard, where he was rebuffed just months earlier, places an order for 60 guns and 20,000 studs. Morrison, his former supervisor, handles the purchase requisition. There is no apology, no acknowledgement that Nelson had been correct. Just a terse official order and a request for prompt delivery. By January 1942, less than 1 month after Pearl Harbor, Nelson's small workshop cannot keep pace with demand. He is receiving orders faster than he can manufacture products. He needs a real factory, more workers, better equipment. He leases a larger facility in San Leandro, several miles south of Oakland. The building sits in the middle of a cornfield, isolated and unimpressive, but it provides space, power, and room for expansion. By March 1942, He employs 20 workers. By June, 50. By September, 150. The factory operates around the clock, 7 days per week. Welding guns roll off the assembly line at a rate of 30 per day. Stud production reaches thousands daily. Every major shipyard on the West Coast now uses Nelson stud welding equipment, and the reports returning are extraordinary. A submarine deck installation that previously required 12 workers and 6 days can now be completed by 3 workers in 1 day. The elimination of scaffolding saves 2 additional days and frees workers for other tasks. The welds are stronger than traditional bolted connections. The wooden deck planks can be removed and replaced more easily for maintenance or repair. At Mare Island Naval Shipyard, submarine construction accelerates dramatically. The yard completes 17 submarines between 1941 and 1945, with average construction time steadily decreasing as new techniques are implemented. Stud welding is not the only innovation, but it constitutes a critical piece of the efficiency puzzle. By mid-1942, stud welding is being used not just for deck attachment, but for dozens of other applications: pipe hangers, cable supports, equipment mounts, bulkhead attachments. Any situation requiring a fastener attached to steel structure, stud welding provides a faster solution. The Navy Bureau of Ships, which initially ignored Nelson's proposal, now studies his process intensively. Engineering teams analyze weld strength, durability, and failure modes. The results confirm what Nelson had known all along. His welds are not just faster than traditional methods, they are actually superior in strength and reliability. The technical specifications vindicate his design. A traditionally bolted connection requires drilling a hole through both materials, threading a bolt, adding a washer, threading a nut, tightening to specific torque, and tack welding the nut. The process creates a mechanical connection dependent on friction and compression. The hole through the steel frame creates a stress concentration point. The bolt can loosen from vibration despite tack welding. Corrosion can attack the threads. The connection represents 6 potential failure points. A stud-welded connection, by contrast, creates metallurgical fusion. The electric arc, controlled at precisely 3000 degrees Fahrenheit for 0.8 seconds, melts both the stud base and the parent material to a depth of 3/16 of an inch. When the arc ceases, the molten metal solidifies into a single homogeneous mass. No holes weaken the structure, no threads can loosen, no mechanical interface exists to corrode. The connection is actually stronger than the surrounding material. Load testing demonstrates that properly executed stud welds consistently fail by breaking the stud itself, rather than separating at the weld interface. The elimination of scaffolding produces cascading benefits throughout the construction process. Without scaffolding beneath decks, electricians can route cables earlier. Pipe fitters can install systems simultaneously with deck attachment. Painters can access surfaces more easily. The submarine interior remains open for multiple trade crews working in parallel rather than sequentially. The time savings multiply exponentially. On November 19, 1942, just 11 months after leaving his $11 daily welding job, Ted Nelson receives a formal visit from a delegation of Navy officers. They arrive at his San Leandro plant unannounced. 5 men in dress uniforms. Captain Robert Harrison, representing the Bureau of Ships, does the talking. Mr. Nelson, we are here to inform you that the Navy has completed evaluation of your stud welding process. We have determined that your invention has saved the United States Navy an estimated 5 million man-hours in submarine and surface ship construction over the past 10 months. That number is expected to increase substantially as more shipyards adopt your technology. He pauses, then continues. On behalf of the Secretary of the Navy and the United States government, I am authorized to present you with a citation for exceptional contribution to the war effort. Nelson is stunned. They rejected his idea. They ignored his proposals, They forced him to quit his job and risk everything to prove his concept. And now, they are presenting him with a citation. Captain Harrison must observe the conflict on Nelson's face. "I understand you submitted a proposal to Mare Island in early 1941, Mr. Nelson. I have reviewed that file. Your proposal was not properly evaluated at the time. That was a mistake, and I apologize on behalf of the Navy. However, your decision to develop the technology independently has resulted in faster deployment than would have been possible through the normal procurement process. Sometimes the best way to serve your country is to ignore official channels and simply solve the problem." Nelson accepts the citation with mixed emotions: pride in his achievement, vindication for his perseverance, but also frustration at the bureaucracy that nearly prevented this innovation from happening. The war continues. Production demands increase. Nelson's company expands again, opening a second manufacturing facility in Camden, New Jersey in March 1943. This East Coast plant supplies shipyards in New York, Philadelphia, Norfolk, and Charleston. By mid-1943, Nelson Specialty Welding Equipment Corporation employs over 400 workers and generates annual revenue of approximately $4 million. Ted Nelson still spends 16 hours daily in the factory, still dresses in shop workers' tan pants and shirts, still draws a modest salary of $1,000 monthly. All profits are reinvested in expansion, equipment, and loan repayment, but his impact on the war effort becomes incalculable. The Navy's estimate of 5 million man-hours saved by late 1942 represents just the beginning. As the war progresses and stud welding becomes standard practice across all naval construction, the time savings multiply exponentially. By 1943, stud welding is being used not just on submarines, but on aircraft carriers, battleships, cruisers, destroyers, and hundreds of smaller vessels. The Essex-class aircraft carriers built by Newport News, shipbuilding and other yards use Nelson stud welding extensively for flight deck attachment and interior fittings. Each carrier requires approximately 20,000 studs. The Navy builds 24 Essex-class carriers during the war. The Iowa-class battleships use stud welding for deck planking, equipment mounts, and armor attachment. The Baltimore-class heavy cruisers incorporate the technology throughout. Destroyer escorts, landing ships, patrol boats. Every type of naval vessel benefits from faster, stronger attachment methods. But the most dramatic impact manifests in submarine construction. Mare Island Naval Shipyard, where Nelson worked and where his idea was rejected, becomes one of the most efficient submarine builders globally. The yard builds 17 submarines during the war, with steadily improving construction times. Portsmouth Naval Shipyard in New Hampshire becomes the champion submarine builder, completing 79 submarines between July 1940 and July 1941-1945. Portsmouth's success is built on multiple innovations, but stud welding constitutes a critical enabling technology. The shipyard's submarine construction time drops from 18 months in 1940 to 6 months by 1943. Stud welding contributes approximately 15% of that time reduction by eliminating scaffolding installation, reducing deck attachment time, and enabling parallel rather than sequential construction processes. Electric Boat Company in Groton, Connecticut, builds 74 submarines during the war. Their adoption of Nelson stud welding in early 1942 correlates with a 22% reduction in hull construction time within 6 months. The company's internal efficiency reports, declassified in 1973, specifically credit stud welding with saving 847 man-hours per submarine in the Gato-class production run. The mathematics of industrial warfare reveal themselves starkly. By 1944, the United States operates 247 submarines in the Pacific Theater. These submarines sink 1,314 Japanese merchant ships, totaling 5.3 million tons of shipping. They destroy 201 Japanese naval vessels, They rescue 500 four-downed aviators. The submarine campaign against Japan's merchant fleet proves more devastating than the strategic bombing campaign. Japan, an island nation dependent on imported resources, cannot sustain its war economy without merchant shipping. By mid-1944, Japanese industry begins collapsing from lack of raw materials. Oil, rubber, iron ore, food. All must be transported by sea, and American submarines make that transportation increasingly impossible. Every submarine deployed to the Pacific earlier means more Japanese ships sunk, more supplies interdicted, more strategic impact. If stud welding reduces submarine construction time by 15%, then Nelson's invention effectively creates an additional 37 submarines without building a single additional hull. Those 37 virtual submarines represent approximately 197 additional Japanese merchant ships sunk, approximately 795,000 tons of additional Japanese shipping destroyed, and an immeasurable acceleration of Japan's economic collapse. But the impact extends beyond submarines. The Liberty ship program produces 2,710 vessels between 1941 and 1945. These mass-produced cargo ships carry the material that wins the war: food for Britain, fuel for Africa, ammunition for France, tanks for Russia. The Liberty ships maintain the lifeline that prevents Allied defeat and enables Allied victory. Liberty ship construction pioneered assembly line shipbuilding techniques. Prefabricated sections built in factories across America are transported to shipyards and welded together like enormous model kits. The average construction time drops from 230 days in 1941 to 42 days by 1943. The record-breaking construction of SS Robert E. Peary takes just 4 days, 15 hours, and 29 minutes from keel laying to launch. Stud welding plays a smaller but still significant role in Liberty ship construction. Each Liberty ship requires approximately 8,000 stud-welded attachments for deck fittings, cargo gear, ventilation equipment, and internal systems. Traditional through-bolting would require constructing scaffolding throughout the vessel's interior and exterior. The time savings from stud welding in Liberty ship construction totals approximately 180 man-hours per vessel. Multiply 180 hours by 2,710 ships, and the result is 487,800 man-hours, saved just in the Liberty ship program alone. Naval construction extends far beyond submarines and cargo ships. The United States produces 27 aircraft carriers, 8 battleships, 48 cruisers, 349 destroyers, 498 destroyer escorts, 203 submarines, 2,710 Liberty ships, 414 Victory ships, 651 tankers, and thousands of smaller vessels during World War II. This represents the greatest shipbuilding effort in human history. At the peak of production in 1943, American shipyards launch 3 new ships every day, 75 ships per month, 900 ships per year. This production miracle is possible only through radical innovations in construction methods: prefabrication, modular assembly, specialized workers, dedicated tools, and faster attachment methods. Stud welding represents one piece of a larger revolution in shipbuilding efficiency, but it is a critical piece. The elimination of scaffolding frees workers for other tasks. The speed of installation reduces assembly time. The strength and reliability of the welds ensure that these hastily built ships can survive North Atlantic storms and enemy attacks. On May 11, 1943, the Secretary of the Navy presents the Nelson Specialty Welding Equipment Corporation with the Army-Navy E Award for Excellence in Production. The E Award was created in July 1942 to recognize companies whose production facilities achieve outstanding performance in manufacturing war equipment. Excellence in quality and quantity determine the criteria. Only approximately 5% of companies engaged in war work receive this honor. The award consists of a pennant for the factory and individual pins for all employees. The ceremony is held at the San Leandro plant with full military honors. Navy officers, Army representatives, and local officials attend. The factory workers, Nelson's employees who have worked grueling hours to meet production demands, receive their pins with pride. Ted Nelson, standing before his workers in his usual shop clothes, accepts the pennant and delivers a brief speech. "We did not do this for awards or recognition. We did this because our country needed it. Every stud we make, every gun we build, helps bring our sailors and soldiers home safely. That is all the reward we need." But the Navy is not finished recognizing Nelson's achievement. Plants that maintain outstanding performance for 6 months after receiving the initial E award are granted a star to add to their pennant. The Nelson Company earns its first star in November 1943. The second star comes in May 1944. By the end of the war, the Nelson Specialty Welding Equipment Corporation has earned 2 E awards with stars, one of only a handful of companies to achieve this distinction. The citations specifically note the estimated 50 million man-hours saved in naval construction. 50 million man-hours. That number requires contextualization. 50 million hours equals approximately 5,700 years. If one person worked 8 hours daily, every single day, it would require over 19,000 years to accumulate 50 million hours. This time, savings results from one simple innovation: a spring-loaded welding gun and a ceramic flux cap. The time savings translate directly into ships in the water faster, more submarines hunting Japanese convoys, more destroyers escorting Atlantic convoys, more landing craft for amphibious assaults, more cargo ships carrying supplies. The strategic impact cannot be measured with precision, but certain conclusions are inescapable. The European theatre requires 32,000 landing craft for the Normandy invasion on June 6, 1944. These landing craft are constructed in shipyards across America, using the same stud welding technology deployed on larger vessels. Each landing craft requires approximately 200 stud welded attachments for equipment mounts, deck fittings, and structural components. Multiply 200 studs by 32,000 craft, and the result is 6.4 million stud welded connections just for the D-Day invasion fleet. Without stud welding, that fleet takes longer to build. Delay the invasion by even 1 week, and weather patterns change, tide tables shift, strategic opportunities disappear. The entire course of the war hinges on timing, and timing depends on construction speed. The Pacific Theatre demands even more landing craft. The island hopping campaign requires amphibious assaults on Tarawa, Kwajalein, Saipan, Guam, Palaleu, Iwo Jima, Okinawa. Each operation needs hundreds or thousands of landing craft constructed, transported, and maintained. The flexibility to mount these operations when strategically optimal rather than when equipment becomes available determines victory or defeat. Beyond military applications, stud welding finds civilian uses that continue long after the war ends. The post-war construction boom transforms America. Interstate highways require steel bridges with thousands of stud-welded connections. Skyscrapers use stud welding to attach metal decking to steel beams. Industrial facilities use it for equipment mounting. Nuclear power plants use it for cable trays and piping supports. The technology Ted Nelson invented to solve a naval construction problem discovers applications in virtually every industry working with steel. Modern stud welding is more sophisticated than Nelson's original design. Inverter power supplies provide precise arc control. Automated systems handle high-volume production. Robotic welders apply studs in automotive assembly plants, but the fundamental principle remains identical. A stud, a flux cap, a spring-loaded gun, and an electrical arc. 1 second per stud. No scaffolding required. On August 6th and 9th, 1945, atomic bombs destroy Hiroshima and Nagasaki. Japan surrenders. On August 15th, 1945, World War II ends. The massive military production machine begins winding down. Contracts are cancelled. Workers are laid off. Shipyards close or convert to peacetime production. The Nelson Specialty Welding Equipment Corporation faces an uncertain future. Military orders dry up almost overnight. The company, which employed over 400 workers at its peak, now faces potential collapse. But Ted Nelson has prepared for this moment. During the war years, he has been contemplating peacetime applications for stud welding. The technology is not limited to shipbuilding. Any industry fabricating steel structures can benefit from faster attachment methods. Nelson pivots to civilian markets. He markets his stud welding systems to construction companies, steel fabricators, and industrial manufacturers. The post-war construction boom provides new opportunities. America is building highways, bridges, skyscrapers, and suburbs. All require steel fabrication and attachment. By 1948, Nelson's company has successfully transitioned to peacetime production. The business is smaller than during wartime, but stable and growing. The company continues innovating, developing new stud designs, improved welding guns, and specialized applications. In 1950, Nelson sells his company to TRW, a large industrial conglomerate. The sale makes Nelson financially secure and allows him to retire from active management, but the Nelson name remains on the product. TRW continues marketing Nelson stud welding equipment, maintaining the brand recognition Nelson built. Over subsequent decades, the company changes hands multiple times. TRW sells to Emhart Technologies in 2000. Doncasters Group Limited acquires Emhart in 2007. Stanley Black & Decker purchases the industrial division in 2018. Through all these changes, the Nelson brand survives. Today, Stanley engineered fastening manufactures and markets Nelson stud welding products globally. Applications have expanded far beyond shipbuilding. Construction workers use stud welding to attach metal decking to steel beams in skyscrapers. Bridge builders use it for guardrail posts and lighting mounts. Nuclear power plants use it for cable trays and equipment supports. Automotive manufacturers use it throughout vehicle bodies for grounding points and trim attachment. But perhaps the most touching legacy of Nelson's invention manifests in the restoration of historic ships. The battleship Texas, one of only 7 remaining ships to have served in both world wars, is currently undergoing restoration at a dry dock facility. The ship requires extensive work to repair corroded hull plates and deteriorated fittings. The restoration team discovers that modern Nelson stud welding equipment is ideal for this work. They can attach new steel plates using the same technology Ted Nelson invented 80 years ago. Similarly, the submarine USS Pampanito, a World War II boat now preserved in San Francisco, uses Nelson stud welding for ongoing maintenance. The boat sits at the Embarcadero, hosting over 100,000 visitors annually. Keeping the old boat safe and functional requires constant attention. Nelson equipment allows the volunteer restoration crew to perform welding work efficiently without requiring certified welders for every task. Ted Nelson lived to see his invention's impact extend far beyond what he imagined that day in 1941 when he sketched his idea in a notebook. He saw stud welding become standard practice in shipbuilding. He saw it adopted by industries worldwide. He saw his name become synonymous with a welding process. He died in 1994 at the age of 89, having lived long enough to witness the end of the Cold War and the transformation of the world his generation fought to preserve. But Ted Nelson never stopped inventing. Even after selling his company, he continued developing new solutions to problems others ignored. He invented a hospital bed that rotated 360 degrees for hip replacement patients, reducing pressure sores and improving recovery times. He designed a glider with an emergency engine called the Hummingbird, providing backup power for safer recreational flight. He held dozens of patents for minor improvements to tools, fasteners, and manufacturing processes. Problem-solving remained his first love until his final days. The statistics of his achievement tell only part of the story. 50 million man-hours saved, 2 Army-Navy E awards, thousands of ships built faster, billions of studs manufactured. But numbers cannot capture the full impact. Behind those statistics were sailors who returned home because their submarine was completed in time to join the fleet. Marines who survived because landing craft were available for their assault. Families who were not torn apart because the war ended sooner. The true measure of innovation is not merely efficiency gained, but lives preserved. How many additional sailors survived because their submarine deployed earlier and intercepted Japanese convoys before those ships reached their destinations? How many soldiers lived because landing craft arrived in time for D-Day? How many civilians were spared because the war ended months sooner, due to accumulated efficiencies across thousands of innovations like stud welding? The mathematics of war prevent precise calculation, but the direction is clear. Faster production equals earlier deployment, equals greater strategic impact, equals shorter war, equals lives saved. Modern military historians analyzing World War II often focus on battles, tactics, and command decisions. They study Midway, Guadalcanal, Normandy, the Bulge, Iwo Jima, Okinawa. They debate Eisenhower's strategy, Patton's aggressiveness, MacArthur's island hopping, Nimitz's carrier tactics. These analyses are valuable but incomplete. Battles are won by soldiers. Wars are won by logistics. The German military possessed superior tanks, sophisticated aircraft, advanced submarines, skilled soldiers, and experienced commanders. Yet, Germany lost. The reason is mathematical. Germany could not replace losses as quickly as the Allies could produce equipment. By 1943, the differential becomes stark. American shipyards launch 3 ships daily, while German submarine construction struggles to replace losses. American factories produce 29,497 aircraft in 1943, while German production reaches 24,807. American automobile plants convert to tank production and build 29,497 tanks in 1943, while Germany produces 5,966. The mathematics of industrial warfare determined the outcome before the first shot was fired. Any nation challenging American industrial capacity faced inevitable defeat regardless of tactical brilliance or individual heroism. The only question was how long the war would last and how many would die before the inevitable conclusion. Ted Nelson's contribution to that industrial capacity seems small when compared to entire shipyards or aircraft factories, but small advantages accumulate. 50 million man-hours saved in naval construction translates to additional ships deployed sooner, additional strategic flexibility, additional operational tempo, additional pressure on the enemy. The cumulative effect of thousands of small innovations, like stud welding, created the overwhelming industrial superiority that determined victory. The lesson extends beyond World War II. Modern conflicts are still determined by industrial capacity and logistical efficiency as much as by tactical skill. The nation that can produce, transport, maintain and replace equipment faster possesses decisive advantage. Technology matters, training matters, leadership matters, but ultimately, mathematics matters most. Ted Nelson understood this instinctively. He saw 4 men struggling with a bolt and recognized that inefficiency repeated across thousands of ships represented strategic vulnerability. His solution was not elegant or sophisticated. It was simply practical. A spring-loaded gun and a ceramic cap. But practical solutions implemented at scale create strategic impact. The story of Ted Nelson contains lessons that resonate far beyond welding or shipbuilding. Innovation often comes from unexpected sources, The best solution to a problem is frequently proposed by someone working directly with that problem, rather than by distant experts or committees. Bureaucracy often resists innovation, not because innovations are flawed, but because innovation disrupts established procedures. And sometimes, the most important thing an innovator can do is ignore the experts, trust their own observations, and build the solution they know will work. Ted Nelson started as an $11 daily welder. He ended as a millionaire industrialist whose technology helped save his country. But he never forgot his roots. He never developed pretensions. He never claimed to be anything more than a mechanic who saw a problem and fixed it. In his later years, when asked about his success, he would shrug and say, "I just built a better mousetrap. The world beat a path to my door. It was not genius, it was just common sense." But common sense applied at the right moment with courage and persistence can change history. That is Ted Nelson's legacy. Not the 50 million hours saved. Not the 2 E awards. Not the global company that still bears his name. His legacy is the proof that one person with a good idea and the determination to implement it can make a difference, even when the experts say it cannot be done, even when the bureaucrats demand following procedures, even when the skeptics dismiss the innovation. The history of innovation suggests that sometimes the most important contribution anyone can make is to ignore the experts, trust their own judgment, and solve the problem they know how to fix. Ted Nelson did exactly that. 80 years later, welders around the world still use his invention every single day. And somewhere, perhaps in a garage or workshop, the next Ted Nelson is sketching an idea that everyone says will not work. But they will be wrong. Because the best innovations do not come from following procedures. They come from people who see a problem, know how to fix it, and refuse to accept no for an answer. Sometimes the best military innovation is telling admirals they're wrong. Ted Nelson proved it, and 50 million man-hours later, the admirals were grateful he did.